Okay, it's 12 o'clock. We'll go ahead and get started for today. Just before we get started, I'm going to pop up our schedule. So, believe it or not, we're most of the way through the semester, and I'm sure you can't believe it. It's been a long semester, I think, for everybody. So, coming up this week, so here's where we are today. Friday, let's see, Friday is one of those funny days. Friday follows a Monday schedule. It doesn't really affect our class time because we have a class on Friday anyway. But for the rest of the things you have going on Friday, whatever you normally do on Mondays, that's what you have to do on Friday, or that's what you're scheduled to do on Friday. We only have 8 classes left, and I'm eyeing this class right here on December the 4th. Our exams start on December the 7th. I'm leaning towards canceling this class. Unless I hear strenuous objections, I'm probably going to cancel because I know you're all going to be getting ready for final exams. And I don't know, it seems brutal to me for us to have a class here, do new material, and have it on your final exam a few days later. To me, that's not really totally reasonable. I might think about having a review session, which I would probably do on a WebEx, just in case people want to leave town for that time between classes and final exam. So I'll kind of think about that. If I get some requests for it, I'll probably go ahead and try and plan one. Otherwise, we'll probably just write this one off. And I think that's a reasonable thing to do. So with our test coming up on Friday, it'll more or less be a repeat of our last test, same style and all that business. Does anybody have any questions before we get going for today? Yep.
We're supposed to have 8 assignments, correct?
I never counted them.
Okay.
Yeah. We do loosely 1 assignment per chapter.
Right.
Yeah.
Okay.
Yeah. So they'll keep going as we cover new material. Yep. I opened one like a couple of days ago, all about resistors. If you can't see it, it probably means that I hit it by mistake. Yeah. Okay, have a look for it if you can, and I'll double check it as well. Because once in a while, like that hide button is really easy to click on by mistake. It's terrible. Bad formatting. Okay, any other questions? Okay, so last day we talked about resistors, we talked about circuits, we looked at resistors in series. We did those quickly, and today we're going to pick up with resistors in parallel. So our idea of a parallel connection is the same thing that we did for our capacitors. And a parallel connection is when things are joined top to top and bottom to bottom. So they're all connected across their tops or across their bottoms. So the ends of resistor R1 go straight into the battery, R2 go straight into the battery, and R3 go straight into the battery. You kind of connect at their tops here, bottoms here, and bottoms here. So those are a parallel connection. Things we know about parallel connections is that they all have the same potential. So potential is all equal in a parallel connection. Then let's think about what has to happen to the current. We know current flows out of the battery, so some current I leaves the battery. The current flows through the circuit, and it's going to hit this place right here. This place here is where 2 wires are joined, so the current has choices. It can move forward, or it can move down. I'm going to say that the current moves down through R1. I'm going to label that I1 for current 1. Then the current that has flowed here, that hits a place where it has a choice of going down or going forwards. So we'll put in those 2 currents. The current comes down through resistor R2. I'll call that I2. And the current coming down through resistor R3, I'm going to call that I3. So in total, this amount of current comes out, and it splits over the 3 resistors. So the total current coming out has to split over the 3 resistors. So potential difference is the same, and current splits, which means that the net current that goes out of the battery is the sum of those three currents. And that's really just conservation of charge. Charge can't go anywhere. We can't invent new charge, and we can't destroy charge flowing through. If we want to think about our Ohm's law, then we know that V is equal to IR. Each of our resistors have the same potential across them. So if V equals IR, then I equals V divided by R. So the current I1 is the potential difference across resistor R1, that's delta V, divided by resistance R1. Likewise, I2 is the potential across resistor 2 divided by R2, and the current I3 is the potential across R3 divided by its resistance. So that's how we can write down the current through each of those resistors. Like we did with our series circuit and our capacitor circuit, we can make an equivalent circuit, and in the equivalent circuit, what we would do is we would take out these three resistors, we would put in a single resistor, and when we connect that single resistor to the same battery, we would get the same current I flowing through the circuit. So there's our equivalent circuit. So the current I here is the same that gets put out by the battery. The potential across this one, and this one are all the same. So that's what we mean by our equivalent circuit. So the potential difference is the current going through the resistor times that equivalent resistance. So that means our net current I would be the potential difference divided by our equivalent. That can come into our equation over here. We see that we've got delta V in the numerator in each of those terms, so we can divide through by delta V, and what we are left with is 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So this is how we find equivalent resistance for resistors connected in parallel. So if you're remembering your capacitor circuits, this was how we added capacitors in series. I'm just going to try turning off another one of the lights. Just finding that screen's a little bit hard to see. Is that any better? Okay. So make sure you don't get your capacitor circuits and your resistor circuits mixed up, because you don't want to get those wrong in the middle of a test. If we think of a resistor as being something like a light bulb, can anybody think off the top of their heads what would be an advantage to a parallel connection versus a series connection?
Each light bulb will be as bright.
Each one would have equal brightness. I agree with that. Could there be another advantage?
You get more light bulbs for the same amount of bulb.
Okay, you could put in more light bulbs. Yep. I think the hand in the back went up first, then we'll come back to you.
If one goes out, the other two will still go on.
Okay, so if one goes out, we keep the other ones. And then did you have something different?
It's the same thing.
Same thing. Yeah, so that's another big advantage to that. So when you're driving, if one of your car headlights goes out, the other one doesn't. That's a good thing, right? You don't want both headlights to go, then you can't see. From my childhood, Christmas lights were always connected in series. So when one light bulb went out, my dad would lose his mind trying to figure which one was gone, so he could fix the whole string, because one bulb goes, the whole strand goes. Current Christmas lights are different, right? Those are connected in parallel, so when one goes, the rest of them are fine. So that's kind of one benefit in a circuit. Okay, let's do an example here of our resistors in parallel. There's not very much complicated I could ask, so we'll do something straightforward. Any questions before we go on? So let's take a set of resistors in parallel. Let's find the equivalent resistance, the current through each one, and the potential across each one. So we'll start by finding the equivalent resistance. So we'll draw an equivalent circuit. In our equivalent circuit, we have the same battery. So delta V is 9 volts. Got a positive end and a negative end. I pop out the 3 resistors and I put in a single resistor. I label it R equivalent. And I know that whatever current flows out of this battery, this current I is the same as this current I. So that's the basis of our equivalent circuit. I'm going to label this resistor R1, this resistor R2, this resistor R3, just so I've got some notation here. To find my equivalent resistance, I have to do my addition for resistors in parallel. So part A, 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3, 1 over 15 ohms, plus 1 over 4 ohms, plus 1 over 8 ohms. You can do a fraction addition if you wish, or you can pop it in your calculator to find 0.442 ohms to the minus 1. Then to find the equivalent resistance, we take the reciprocal of both sides. To find 2.26 ohms. So that's the equivalent resistance of that circuit. I get a little cramped at the end, so that's 2.26 ohms. So if the handwriting is hard to see, that's what that's supposed to be. All right, that's part A. Part B is find the current through each resistor. So what I know about my current is that current will get to this point and it will split. Current I1 will come through resistor R1. Some of the current will go forward when it gets to this point. Current I2 will come down here, and current I3 will come down here. I know I can use Ohm's law, V equals IR, to figure out my currents. If I want to do that, I should figure out my potentials. So I'm going to do part C before I do part B. I'm going to write down my potentials next. In part C, the potential across each resistor, delta V1, so this has delta V1, delta V2, and delta V3. Delta V1, delta V2, and delta V3 are all the same as the battery 9 volts because they're connected in parallel. So any two connections in parallel have to have the same potential. So parallel, same potential. Okay, now we're good to go. We can figure out the current through each of those 3 resistors. Back to part B. So my current I1 is my potential across resistor 1 divided by resistance R1. 9 volts over 15 ohms gives us 0.6 amps. I2, same equation. 9 volts over 4 ohms gives us 2.25 amps. I3, potential 3 over resistance 3, 9 volts over 8 ohms to get 1.125 amps. Any questions here? Pretty much just a plug and chug. What we might notice here, if you look at the resistances and the currents, so resistor 1 is the biggest and it has the smallest current. So resistance talks about how difficult it is for current to flow through an object. If your resistance is big, it's hard for current to flow through, so less comes through this branch. If your resistance is small, it's easy for current to flow through, so the most will come through this branch, and we get the biggest current through that branch. So physically, that's what's going on there. Okay, questions about this one? Okay, so when we did capacitors, we did series, parallel, and combination. We're going to do the same thing here. We've just done series, we've done parallel, now we'll do a combination circuit, and then we'll get into our general analysis technique. here's our combination circuit. The first thing we'd like to do is find the equivalent resistance. Then we'd like to find the current through each resistor, and we'd like to find the potential across each resistor. So we're going to break this circuit down the same way we did with the capacitor circuits. We'll identify things in parallel and series. We'll apply our equations until we get to one final circuit. We'll do our diagrams as we go, and do our calculations as we go. So the first thing we ask is, can we identify any two resistors that are clearly in series or clearly in parallel? To be clearly in series, they go right from one resistor to the other resistor, all in a row with no branching in between them. I don't think that applies to anything in this circuit. So we don't have two resistors in a row here. For a parallel connection, do we have any two resistors connected top to top and bottom to bottom? I would say that applies to our 4 ohm and our 8 ohm. So our first step to break down is that these two resistors are connected in parallel. Okay, so I'm going to call this one R1, this one R2, and this one R3. Oops, R3. I know that R1 and R2 are connected in parallel. So my equivalent circuit will have R3 here, my first equivalent here, and the rest is wires. So this is this is R3. And this is going to be the equivalent between 1 and 2, so I'll call it R12. If they're in parallel, I know that 1 over R12 equals 1 over R1 plus 1 over R2 equals 1 over 4 ohms plus 1 over 8 ohms. 1 over 4 plus 1 over 8, that's 3 over 8 ohms. Do the reciprocal of both sides. R12 is 8 ohms divided by 3. You can leave it as 8 over 3 or write 2.67 ohms. Okay, so there's my first connection. My next connection, so these two were in parallel. As you're going through, you don't have to make notes, but you should kind of make a mental note that in parallel they have the same potential. Okay, so that'll help us afterwards as we go through. For our next connection, we only have 2 resistors left. How are they connected? These are straight in a line. These 2 are connected in series. So these are a series connection. Make our mental note that series means same current. So R3 and R12 are a series connection. We will draw our equivalent circuit. Here's our equivalent. And we know our equivalent is those resistors added up, R3 plus R12, 15 ohms, plus 2.67 ohms to give us 17.67 ohms. So there's our answer to part A. That's the equivalent resistance of this set of resistors. Make sense? Okay, so now to answer B and C, and we'll tend to do B and C together as we work through. We're going to start working backwards. So if we look at this circuit right here, this equivalent resistance is 17.67 ohms. We know that a 9-volt battery is connected to that resistor, so I can find the current that flows through this circuit. So a current I flows through. My current I is going to be the potential, delta V, divided by the equivalent resistance. 9 volts divided by our equivalent, 17.67 ohms, gives us 0.509 amps. Any questions there? Okay, so now we come back up to the previous step. I could draw on that diagram, but I don't think I will, just because I think it'll get a little bit too messy. So I'm going to redraw this diagram and apply what I just figured out. So I'm going to back up a step. There's my 9-volt battery. there's my R3, there's my R12. These are a series connection. They have the same current. So the current that goes through each of those two resistors is the I that we found in the previous step. So R3, that has a current I equals 0.509 amps flowing through it. The potential difference across that resistor, delta V3, is I3 times R3, 0.509 amps, times that resistance, 15 ohms. That potential difference is 7.64 volts. Okay, so I've answered B and C for the resistor labeled R3. That bit is done. I've got the current and potential. Through resistor R12, the current going through this equivalent resistance is the same, 0.509 amps. With the current flowing through this and the resistance, I can find the potential across this equivalent resistance. Delta V across R12 is I12 times R12, 0.509 amps. R12 was 2.67 ohms. So that potential is 1.36 volts. There would be a second way to figure that out. We know that 9 volts is put out into the circuit, 7.64 is across this one, so the rest of the potential has to be across this one. It's kind of another way to think about it. Okay, are we good to here? All right, we said we've already dealt with R3, which means we have to deal with R1 and R2 next. So we have to back up another step. So we came to this step. Our previous step now is this one. R12 is the parallel equivalent of R1 and R2. So we're going to come back to this circuit. I'm going to draw that again so I don't have to scribble on that top one. So I will back up. There's my 9-volt battery. There is my R3. Here is my R1. Here is my R2. And there is the rest of my circuit. Here is R3, we've got that one done. Here is R1, here is R2. We know that resistors connected in parallel have the same potential. The potential across our parallel equivalent was 1.36 volts. So the potential here is 1.36 volts, and the potential here is 1.36 volts. Okay, things in parallel have the same potential. So for my resistor R1, I know that the potential difference, delta V1, is 1.36 volts. To find my current I1, it's going to be the potential divided by the resistance, 1.36 volts, divided by 4 ohms, to give us a current of 0.34 amps. So that's R1 taken care of. Now we'll take care of R2. Potential across R2 is delta V2. That's also 1.36. Because they're in parallel, they have the same potential. The current flowing through at I2 is delta V2 divided by R2, 1.36 volts divided by 8 ohms to give us 0.17 amps. Okay, make sense? This stuff is probably not hard, but it can be a little tedious because you got to go through it step by step and not get confused. The key part is remembering the series, the same current, parallel, the same potential. So this method, this equivalent circuit method, is a fair way to analyze circuits. You can do it for most circuits, but you can't really do it for every circuit. Sometimes they're really complicated, and it's harder to make a plain parallel series breakdown because of the connections. So we're going to move to the generalized approach, which maybe some people did in high school, but not everybody, and at any rate, it was probably a while ago. So our general approach is a Kirchhoff's law approach. We've used these ideas already as we talked about resistors and the current and the potential. Now we're going to formalize them and we're going to call them laws. So Kirchhoff's current law is also called a junction law. So the definition of a junction is any place where two or more wires meet. So in this picture, a junction is right here. So there's our junction. And the current law says that the total amount of current into a junction is equal to the total amount of current out of a junction. So net current in equals net current out. That's just conservation of charge. Okay, we can't invent charge and we can't destroy charge. So if in this circuit we had a current I1 flowing into this junction, it means some of the current would flow out, we could call that I2, would flow out this branch, and some of the current would flow out this branch, we could call that I3, and our current law says that the net current into a junction equals our net current out of a junction. In terms of an equation, here we would say I1 equals I2 plus I3. And this is just conservation of charge. Okay, so as we analyze circuits, we'll identify junctions, we'll label currents in, currents out, and we'll write down this as an equation. So that'll be one step in our analysis. The second step is called Kirchhoff's potential law, or the loop law, or the loop rule. So sometimes it's current rule and potential rule. And what the loop rule says is that the net potential around any closed loop, the net change in potential has got to be zero. So every circuit element in a circuit would have a potential difference across them. So we might label them delta V1, delta V2, delta V3, and delta V4. So these are just unknown circuit elements. They might be capacitors, they might be resistors, they might be batteries, whatever they are, there is a potential difference across them. If we identify any closed loop, that loop is pretty obvious for this circuit. So here is a loop. When we add up the total current around that closed loop, it has to sum to zero. So for any closed loop, the net change in potential is zero. In terms of an equation, we would say delta V1 plus delta V2 plus delta V3 plus delta V4 equals zero. Okay, so those are our two rules. This one is conservation of energy. Any energy put into the system is also put out from the system. So potential put in equals potential put out. If you look at this equation, we see we're adding up four things to get zero. That means some of these things have to be positive and some of these things have to be negative. So some things supply potential, like batteries. Some things use up potential, like resistors. Okay, so our next step is how do we tell what potentials are positive and what potentials are negative? So any questions before we keep going? And I think the idea of the positive and negative potential, it can be a little bit subtle, and it can be easy to skim over it and just expect students to know what's positive and what's negative, but there is a way to tell. So let's look at that bit next. So does a potential increase or decrease? It's a very good question. So let's look if we have a circuit like this. We've got a battery here, we've got a resistor here. What happens inside the battery is that there's a chemical reaction that makes positive charge move through the battery, flow out of the positive terminal, and go around the circuit. We've talked about that a bunch of times already. So in our circuit, we will get a current flow. So there is our current flow I. Our battery, as we go from here to here, This is a negative terminal, that's got low potential. This is a positive terminal, this has got high potential. As we go from here to here, the potential increases. So this is the potential across the battery, delta VB. And this has to be positive because we go from negative to positive, it increases. So delta V of the battery is positive. That means it supplies energy. Okay, so there's that bit. As we come to our next element in the circuit, this is a resistor. So this end is positive. These stretches here, they indicate ideal wires. We say they don't have any resistance at all, so we can't get any potential drop across the resistance. So these 2 points have to have the same potential. Okay, so if this one is a high potential, this one is also a high potential. These 2 points are connected here to here. There's no potential loss across this battery. So if this one is a low, this one is also a low. So across the battery, or across the resistor, that has a potential difference from here to here. As we go around the circuit from here to here, we go from a high potential to a low potential. That's a potential decrease. So this is delta V for the resistor. That delta V is negative because we go from high to low. There's a decrease in potential. This dissipates energy. So if this was a light bulb, it would light up, give off energy as light. Most resistors, they get warm, they give off energy as heat. So then when we write down our loop rule, we say delta V of the battery plus delta V of the resistor equals 0. This one's positive, this one's negative, this equation's okay. All right, so some of them are positive, some of them are negative, and you do have to figure out what's positive and what's negative. Okay, any questions about that bit? So, there's the physics ideas behind it. We also have a way to do this more in practice. So, when we get a circuit diagram like this, one of the first things we do in our circuit diagram is we identify the current flow, and we draw current flow coming out of the positive ends of batteries. So typically that's what we're gonna do. So current flows out of the positive end. So we label our current in the battery, our current going through the circuit. That's step one. Step two is we identify the loop. So we said around any closed loop, the potential is gonna sum to 0. So we have to identify the loop. That would be the next thing we do. So let's say this is a loop. To make life easy, you frequently draw your loop direction to match your current direction. You'll see that this doesn't always work, but that's how we tend to do it because it makes the equations easier. So your loop will tend to follow your current direction. So we draw the current, we draw the loop. The next thing we can do is we can identify the positive and negative ends of the resistor. Another way to identify the positive and negative ends is we know that the current will flow with the electric field. Okay, so electric field will match the direction of current flow, and electric field points from high to low potential. So in our resistor, the electric field will be the same direction as current, it will point down. If the electric field points down, it goes from high potential to low potential. So if you're trying to identify the positive and negative ends of a resistor, we know that current flows from high potential to low potential. That's how you can draw those ends. If you don't like the idea of labeling the high and low ends of the resistor, you don't have to do it. Okay, so this is for people whom it helps. If it doesn't help you, you don't have to do it. Because there is another way to figure out the signs. So when we write our loop rule here, let's start with the battery. As we come around our loop, we see we go from negative to positive, low potential to high. That's a potential increase, it gets bigger. So when we start with our battery, we say plus, that's an increase, the potential of the battery. Okay, that's how we start. Plus for two reasons, or two practical reasons. So we say plus here. Reason number one is it goes from, current goes from, or our loop goes from negative to positive, so from low to high. So there's our physics reason why we would write that as positive. The other reason, and this is just a rule of thumb to help you out when you're trying to remember how to do things, if your loop matches your battery direction, that's a potential increase. So if your current goes the right way through the battery, so your loop is this way, your current is going through this way, if the current is going through the right way, that's a potential increase. So if your current loop is going that way. Then for our resistor, on the resistor end, our current goes from positive to negative. That is a potential decrease. And potential is I times R, and that has to sum to 0. So right here, it's negative because it goes from plus to minus, so from high to low. Or because anytime our current goes the right way through a resistor, and the right way means it matches the loop, so if it goes the right way, we get a potential drop across the resistor. Okay, so if things go the right way, they act as expected. If they go the wrong way, they act the opposite way. I will talk about this as we go through examples. Okay, any questions to hear? It probably feels really vague right now, but we will see in detail. Okay, so let's do an example, and what we'll do is we'll go back to that combination circuit we just did, and we'll analyze that circuit. So let's start going through the process. Here's our circuit. At this point, we already know the answers, but let's go through the process anyway. So the way we start is that the first thing we do is we identify and label all of the currents. So you say that the current comes out of the positive end of the battery. So current flows out here. Our picture already labels that as current I, so I'm going to stick with calling that I. Our current gets to point A, flows through the 15 ohm resistor, and then hits this dot right here. This is a junction because this wire is meeting these two wires. That means that the current has to split. So current comes in, part of it comes up and goes through the 4 ohm resistor, part of it comes down and goes through the 8 ohm resistor. So the current has to split. Now I have to label those currents. I'm going to call this current I1, and I'm going to call this current I2. So there's step one of the problem, is draw and label your currents. So when I1 and I2 meet up down here at this junction, they come back together, and current I continues to flow around the circuit. So we've identified the current. The next thing we have to do is identify our loops. Okay, so we know that we're going to be doing the loop rule. We're going to be summing the potentials around closed loops. So there are two kind of obvious loops that we could pick here in this problem. So we can pick this inside loop here. So this can be our loop 1. It's not that pleasant looking, but it's still a perfectly valid loop. So this is loop 1. Okay, so everywhere inside this closed circuit, we're going to add up all of those elements. And then the other one we could pick is up here. We can call this loop 2. Usually as you're doing these problems, the loops kind of jump out at you. So you can see a couple of open areas. Those open areas are where you draw your loops. You still good? Yep.
For loop 2, how do you know the direction? Because the I is split into 2 ways, so couldn't it be the other direction as well?
Okay, that was an excellent question. If not everybody heard it, it was basically, how did I know to pick this as my direction for loop 2? The answer is I didn't. I had to pick one or the other. I picked this one. If I picked the other direction, I would get the same result. It's just the signs would be switched. Okay, so we'll talk about, like, when I write down this equation, I'll show about how those signs would have been switched, so we'll address that when we get to it. So that's a good question. You don't really know the directions of your loops. As best you can, pick it to match one of the currents. Okay, so that was why I picked the direction of loop 1, because it does match the currents here. Loop 2, I have to go against one of those currents, and we'll see how to deal with that. Okay, so we'll write our junction law first, and our junction law says that the net current into any junction has to be equal to the net current out of the junction. So we'll write our current law. So the net current into our junction here is I. The net current out is I1 plus I2. So there's our current law. Next, I will write down my two loop rules. And I'm going to give myself lots of space just for doing algebra. So I wrote down this loop first. I called it loop 1. I'm going to write down this rule first. So for loop 1, if I like the idea of labeling the ends of my resistors, my current flows through from left to right. So this would be the positive end, that would be the negative end. Current I2 flows through this way, plus to minus. So I've labeled the ends of my resistors if I like that way of doing it. So for loop 1, I'll start with my battery. My loop goes around, my loop direction matches my battery direction. I go from a negative or a low potential to a high potential. This is a potential increase of my battery. So I'm going the correct way through my battery. So I get plus 9 volts. I hit my first resistor, the 15 ohm resistor. I go from the positive to the negative, the high to low. That would be a potential decrease. The other way to do it is I see that my current goes with the loop. So when the current and the loop are in the same direction, you get a drop across a resistor. So that's minus current I times my 15 ohm resistor. I'm going to leave my units in my equation. That can look a little bit tangly. If you prefer to leave your units out here in this step, that's absolutely fine. Coming around my loop, the next thing I get to is my 8 ohm resistor. I go from high to low, and my loop matches my current, so that is a drop across resistor 2. That difference, that potential difference, is the current I2 times my resistance 8 ohms. That's all of the things in that loop that have a potential difference, so they have to sum to be 0. Okay, are we good with loop 1? Now we'll get to loop 2, and we'll talk about that direction and how we pick that direction, or what we do about that direction. So for loop 2, we can identify the positive and negative ends of the 4 ohm. The current goes through this way, so from here to here. Loop 2. As we come around to the top resistor, so our loop comes this way across the top one. It goes from left to right, from high to low potential. The loop and the current match, so that's a drop across the 4 ohm resistor, minus I2 times 4 ohms. Then when we get to the bottom resistor, as our loop comes around, the loop goes from a low potential to a high potential. Low to high is a potential increase. So across this one is a potential increase. And then if we look at it, our loop goes to the left, our current goes to the right. We're going the wrong way through that resistor. The loop and the current don't match. That also corresponds to writing down a potential increase. Okay, so as we go from negative to positive, that's a potential increase of I2 times 8 ohms equals 0. If we had taken our loop the other way, then we'd be going the wrong way through the 4 ohm resistor. That would be an increase, plus I1 times 4. You'd be going the right way through the bottom resistor. It'd be minus I2 times 8. We'd get the same equation, just multiplied by negative 1. So you get the same equation, even if you took the loop the opposite way. All right, any questions about these 3 equations? So from here, I would say that all of the physics is now done. The next thing we just have to do is some algebra. We've got 3 things we don't know, we've got 3 equations, we can figure out these equations. So where I'll go next is I'm going to look at my loop 1 equation. I'm going to rearrange it so it says I equals something in terms of I2. I'm going to do the same thing with my loop 2 equation. So I'm going to get I1 in terms of I2. I'm going to pop them back in here and I'm going to solve for my currents. So there's my strategy. So for loop 1, I times 15 ohms equals 9 volts minus I2 times 8 ohms. I is equal to 9 volts over 15 ohms minus I2 times 8 ohms over 15 ohms. If you simplify that a little bit, I is equal to 0.6 amps, subtract 0.533 times I2. Okay, so I've rearranged that to solve for I1 in terms of I2. I am keeping an eye on the clock. I'm not going to keep you over time, but I'm going to try and get the equations set up before we have to quit, certainly. Okay, I'm going to do likewise here. I found for I in terms of I2. Now I'm going to find for I1 in terms of I2. So I1 times 4 ohms equals I2 times 8 ohms. This makes sense. The potential across the two of them is the same because they're connected in parallel, so this looks sensible to us. That means I1 is equal to I2 times 8 ohms divided by 4 ohms. So I1 is twice I2. So now I've got an expression for I and I1 in terms of I2. I'm going to go back to my current law and use that one to solve the problem. Okay, so back in my current law, I have I right here, but I is equal to 0.600 amps minus 0.533 times I2. That equals I1, but I1 was 2 times I2 plus I2. Okay, so I made my substitutions there. If I do my algebra here, and I won't write out my algebraic steps here for expedience, I get I2 equals 0.170 amps. Same as what we found in our last problem. Okay, so to do the algebra, we get our I2. After we get our I2, we can go back to our equation for I and figure out I, 0.509 amps. And we can look at our equation for I1 and find our I1. I1, 0.34 amps. Okay, so that's it in a nutshell. That takes us up pretty much to time being over. So we'll quit there for today, and we'll do more of this on Monday.